Last time we have started with the topic of boiling, and I first of all I described to you when boiling will occur. Then I classified two types of boiling. I said there is pool boiling and flow boiling, and then we focused our attention on pool boiling, and I identified various regimes or various regions in pool boiling, and I drew a typical pool boiling curve while identifying those regions. What were those regions? They were first of all the natural convection region, then the nucleate boiling region, and the third one was the film boiling region. Even in the film boiling region there were two parts, one part which I called the transition boiling region, in which we have a transition from nucleate to stable film boiling, and the second part which I called as stable film boiling. I also identified one important point on that pool boiling curve, and I said that point is called the peak heat flux or the critical heat flux. And I told you why that point is important. If heat flux is the parameter that is under your control, and if it is the quantity that is varying, then if one goes past the critical heat flux, then the temperature difference T W minus T S, the wall temperature minus the saturation temperature, will shoot up from a value which might be 10 or 20 degrees centigrade to perhaps a few 100 degrees centigrade, even maybe 1000 degrees centigrade, and there is a possibility that the heated surface may get damaged. And that is why whenever heat flux is the controlling factor, and it is in many situations, then one would see that the peak heat flux is not exceeded in order to prevent any damage to the heating surface. Now, today we are going to look at a number of correlations, equations to use in doing calculations in pool boiling. We will focus our attention on saturated pool boiling, correlations in saturated pool boiling. So, today we are going to look at correlations in saturated pool boiling. By saturated pool boiling, I mean that we have of course a pool of liquid, and in that pool of liquid the water or the liquid, whatever it is at a certain pressure and at a temperature, saturation temperature corresponding to that particular pressure. So, that is what we call as a saturated pool. It is at a particular pressure and it is also at the particular saturation temperature corresponding to that particular pressure. We add heat to that liquid, just as I had indicated in the sketch last time. We go on adding heat, and we will go through the various regions of boiling, and in those various regions what are the correlations to use. So, the first region which we have identified is natural convection, that is region 1 last time. Now, in region 1 I have mentioned it, but let me repeat, change of phase does not occur at the heated surface. That is the point which I made to you last time. The heated surface is at the bottom, the change of phase does not occur there. What happens is, because of the small temperature difference, the water gets slightly superheated, water or the liquid whichever we are talking about gets slightly superheated, maybe by a degree, 2 degrees or something like that. The superheated liquid will obviously have a lower density, it is going to rise and will set up a natural convection pattern in that pool of liquid. The superheated liquid then eventually will reach the free surface of the pool, and at that free surface you will get evaporation. So, that is the nature of this region. Obviously, if there is no change of phase, no vapor formation inside the liquid, it is clear that all you have is a natural convection single phase phenomenon taking place with superheated liquid. And therefore, it is also obvious that all the correlations which we have studied earlier in single phase natural convection will be valid in this region. So, that is the point I want to make first of all, that all single phase, let me write that down, all single phase natural convection correlations are valid in this region. So, there is nothing new to do. We can go back to our chapter on single phase natural convection, look up the various correlations. We have got correlations, for example, for horizontal tubes, we have a correlation for a heated surface facing upwards, we have correlations for other situations also available in the literature. Any one of them is valid depending upon the heated surface that we are talking about in this particular situation. For example, let us say we have got a situation of, as an example, let us consider that we have horizontal wires or cylinders which are being heated in a pool, a horizontal wire, a horizontal cylinder which is inside a pool of liquid. Then if boiling is going to take place and it is the natural convection region, the relationship between heat flux and temperature difference T W minus T S are as follows. Now, I am not going to read these out because you have done these correlations earlier in natural convection. What is the difference between what the way these are written and what was written earlier in natural convection is, when we were studying natural convection, these relations were given in terms of a Nusselt number as a function of Rayleigh number and Prandtl number. Now, following the practice adopted in boiling, we have written these relations in terms of a heat flux equal to something multiplied by temperature difference multiplied by the particular relationship. So, let me just illustrate what I mean. What I mean is the following. Earlier, the relationships were of the form N U D is some function of Rayleigh number and Prandtl number. These were how the relationship was given earlier. Now, what is Nusselt number? Nusselt number is nothing but H D by K, which is a function of Rayleigh number and Prandtl number, and H is nothing but Q by A divided by T W minus T S multiplied by D by K equal to a function of Rayleigh number, Prandtl number. So, these relationships which I am showing you are written in the form Q by A is equal to K by D multiplied by T W minus T S and multiplied by the functional relationship which is available from the correlation in natural convection. This is how these relationships which I am showing you are put down. They are equivalent obviously, as I have shown to the relationship given earlier. So, let me again show these now. If the geometry is a horizontal wire or cylinder, the relationship between heat flux and temperature difference are as follows. Properties again as previously would be evaluated at the mean film temperature T W plus T S by 2. If the geometry is something else, say for example, a heated plate facing upwards, go back to the single phase natural convection chapter, look up the correlation there, Nusselt number as a function of Rayleigh number and Prandtl number, whatever it is, and convert it into this form Q by A equal to K by L into T W minus T S into something. So, you should be able to write down such relationships depending upon the particular geometry you are studying. I have given one as an example. Now, let us move on to region 2. In region 2, we have nucleate boiling. Nucleate boiling means bubbles now form at the heated surface. It is now a situation in which a typical situation is at particular sites on the heated surface, a bubble is formed, it grows in size. Then when it grows to a certain particular size, because of buoyancy forces, it detaches from the surface and rises. Another bubble forms at the same site, again grows in size and again rises. and this phenomenon takes place at a number of sites. As you go on increasing the temperature difference, the number of sites at which this happens goes on increasing. The frequency with which the bubbles form per minute at a particular site also goes on increasing. So, that is the nature of nucleate boiling, and we have described it last time. Now, many correlations have been developed by various investigators over the years for this particular phenomenon, and I am going to give in this lecture one particular correlation. The correlation that I am going to give is a correlation given by Rosenau. It is called the Rosenau correlation, quite appropriately. Now, let me just read out the correlation, then I will describe what are the parameters in this correlation. The correlation is, on the left hand side, CPL multiplied by T w minus T s upon lambda, that is on the left hand side. This is a dimensionless parameter, and you know the symbols, what they mean. CPL is going to be the specific heat of the liquid, T w minus T s is the temperature difference between the wall and the saturation temperature of the liquid, divided by lambda, which is the latent heat of vaporization. It is a dimensionless number making up the left hand side of the equation, equal to KSF. KSF is a constant which I will talk about in a moment, again multiplied within square bracket by a quantity Q by A, that is the heat flux being supplied, divided by mu L lambda. Mu L is the specific, is the viscosity of the liquid, lambda is the latent heat of vaporization. Within the square root sign, square root of sigma upon G, rho L minus rho V. Sigma is the surface tension and G is the, of course, the acceleration due to gravity, rho L the density of the liquid, rho V the density of the vapor. The quantity within the square bracket is also a dimensionless number, keep that in mind. It is often called also some kind of a Reynolds number, a bubble Reynolds number. It is sometimes referred to as a bubble Reynolds number. One can attach some physical significance to it. And then the third dimensionless number is the Prandtl number PRL, which is the Prandtl number of the liquid. So, what Rosenau did was to correlate data for a wide variety of liquids which had been obtained by various investigators, and show that these three dimensionless parameters which I have mentioned could be correlated through an equation of this form. Now, let us talk a little about this correlation. First of all, again let me go back to the symbols. I will not go through these in detail, because I have taken them up one by one. CPL the specific heat of the liquid, T w minus T s the temperature difference between the surface and the liquid saturation temperature, lambda the latent heat of vaporization, Q by A the heat flux in watts per meter squared, mu L the viscosity of the liquid, sigma the liquid vapor surface tension, rho L the density of the liquid, rho V the density of the vapor. These are all known symbols to you. PRL the Prandtl number of the liquid. N the constant at the end, PRL to the power of n in that equation is an exponent on the Prandtl number. From the experimental data, it is found that for water the data fits best if n is taken as 1. For other liquids, the experimental data fits best if n is taken as 1.7. So, n has two values depending upon the liquid which is being boiled. And finally, we have a constant KSF, a constant whose value, it is not the whole value, whose value depends upon the surface liquid combination. And this the value of KSF was determined by Rosenau and by others for a variety of surface liquid combinations. So, let me just show you a table in which values of KSF are tabulated. Here is the table, it is available in various books. I have just given, and there are more values of KSF for other surface liquid combinations as well. So, on the left hand column is the surface liquid combination, the right hand side is the value of KSF as obtained by correlating the experimental data. What do we have typical values? If the surface is copper and water is the liquid being boiled, 0.013, for platinum water 0.13, for nickel water 0.006, for brass and water 0.006. Then there are 4 values here for stainless steel and water, with the stainless steel surface being subjected to different surface treatments. So, the first one is stainless steel and water with the stainless steel surface mechanically polished 0.0132, stainless steel and water where it is chemically etched 0.0133. Third one, stainless steel and water where the stainless steel is coated with Teflon 0.0058, and finally, stainless steel and water where it is ground and polished 0.0080. Notice that as the stainless steel surface becomes smoother, which is the case in the last 2 surfaces compared to the first 2, the first 2 it is mechanically polished or chemically etched, the last 2 it is Teflon coated and ground and polished. Notice that in the last 2 cases the value of KSF is about half compared to the value earlier. So, the value of Q by A for the value of T w minus T s for the same Q by A will be half the value that you get for the mechanically polished surface. Keep that in mind. Not half, I should not say that, because there is a cube 1/3 power on the Q by A, but it will be less. So, these are typical values of KSF, and there are values of KSF for other surface liquid combinations as well. Now, in this correlation, let me make some remarks on this correlation. First of all, the correlation was developed for horizontal wires. The Rosenau correlation is used for horizontal wires, horizontal tubes, horizontal plates. All properties are evaluated at the liquid saturation temperature. And the value of constant KSF, I have already discussed what it means and shown you typical values. Keep in mind that the Rosenau correlation, what it is basically saying is that Q by A, if I cube both sides of the Rosenau correlation, what the Rosenau correlation is saying is, for a given liquid, for a given surface and a liquid, the Q by A is proportional to T w minus T s to the cube. That is what the Rosenau correlation is saying. It is useful to keep this dependence in mind. Now, let us go on to the next point on the curve. The nucleate boiling region ends when we reach the point A on the pool boiling curve, which I mentioned to you last time. And what is that point A? The point A is what we called as the critical or the peak heat flux. Now, for this particular point, a number of equations have been developed to calculate the critical or the peak heat flux. I will give you a few of them. The first one that I am going to give you is a correlation, an equation I should say, developed for an infinite horizontal plate facing upwards. That is something like this. I have a plate, let me draw it on a separate paper. The first equation is for a plate like this, which is heated facing upwards and receiving heat, and there is a pool of liquid above it. like this, and it is supposed to be infinite in extent. Based on a stability analysis, a hydrodynamic stability analysis, Kuteteladze and Zuber derived an expression for the peak heat flux for an infinite horizontal plate, which is of this form: Q by A critical is equal to pi upon 24 lambda rho v multiplied by sigma g rho L minus rho v upon rho v squared to the power of 1 by 4 multiplied by rho L plus rho v upon rho L to the power of half. It is a classical expression derived based on hydrodynamic stability considerations. All properties are evaluated at the saturation temperature T s of the pool. Now, for most situations, the second term rho L plus rho v divided by rho L to the power of half, for most situations this second term here tends to be almost unity. And if you put that simplification in, then the expression reduces to the simpler form: Q by A is equal to pi upon 24 lambda rho v in the square bracket sigma g rho L minus rho v upon rho v squared, the whole thing to the power of 1/4. This would be the value of the critical heat flux, and this expression is very widely used. There is a slight modification to this expression, which was derived a few years later, and I am going to give you that. If the plate is finite sized, not very small, but finite sized, then for a finite sized horizontal plate, Lienhard and Dheer showed that the expression was slightly modified. Instead of having a pi by 24, they derived a constant 0.149. The rest of the expression is the same that we had earlier. So, Q by A with the derived by them was Q by A critical is equal to 0.149 lambda rho v to the power of half multiplied by sigma g rho L minus rho v, the whole thing to the 1/4 power. So, we use this expression or the earlier one, depending upon which one we prefer. There is a 10% difference or so between the two. This expression derived by Lienhard and Dheer is valid so long as the plate is not too small or is, shall we say, large, and the way to show it is to calculate the dimensionless quantity L into bracket g rho L minus rho v upon sigma to the power of half, and to show that this quantity is greater than 2.7, where L is the characteristic dimension of the plate. So, what one finds for typical liquids is that unless the plate is extremely small, a few millimeters or so, this expression generally you will get a value greater than 2.7. So, for calculating peak heat flux, the preferred expression is the expression given by Lienhard and Dheer, which is Q by A equal to 0.149 lambda rho v to the half into bracket sigma g rho L minus rho v, the whole thing to the power of 1/4. This is the expression that is nowadays preferred. There are expressions for other geometries also. I am not giving them here, but there are expressions available for other geometries like horizontal tubes, etc., for the peak heat flux. Now, finally, we come to the boiling region, I mean the film boiling region. First, we have the transition boiling, and you recall my mentioning to you that transition, or describing to you that transition boiling is the region in which, the Q by A value decreases as T w minus T s increases. And this particular thing happens, this situation occurs because it is a region in which part of the surface is covered by a film and part of the surface nucleate boiling is occurring. And when the film boiling takes over suddenly, then the vapor having a low thermal conductivity puts an additional thermal resistance in the path of the heat flow. So, for a certain T w minus T s, you require you get a lesser Q by A flowing across the vapor film. That is why one gets a decrease in the Q by A with increasing T w minus T s. Transition boiling is not something that is widely studied, and the reason is it is not something that occurs that often in practice. It has been studied by a few investigators. There are some papers showing curves of what you get for different liquids and surfaces, but no satisfactory correlation which can go across various sets of data has ever been obtained. So, we will not give any correlation at this in this particular for this particular phenomenon. The next in the same region is the stable film boiling region, and here for stable film boiling we will give a correlation which was derived first by give an expression which was derived first by Bromley. The particular expression which I am showing you is valid for a horizontal tube. So, Bromley derived this expression for the geometry of a horizontal tube, something like this. That means, we have a horizontal tube. Let me draw one, draw a cross section of the horizontal tube. Let us say this is a horizontal tube sitting in a pool of liquid. This is a pool of liquid. Sitting in a pool of liquid, heat is being supplied like this to the pool of liquid, and the temperature difference is large enough that we have got stable film boiling. So, what will happen? What will happen is you will get a film of vapor all around that tube forming something like this. Let me draw a film. I will draw an exaggerated thickness again. We will get a film of vapor like this forming around the tube, flowing upwards because the density of the vapor will be less than that of the liquid. So, this is vapor flowing upwards and then forming some kind of a pattern as it goes out of the liquid upwards. So, this is what we will get if you have got stable film boiling. A film of vapor all round the heated surface, the film of vapor rising and then going up as a plume at the top. That is what you will get. So, this is what we are talking about. Now, notice the similarity between this and what we saw in film condensation. There we had a film of liquid flowing downwards. Now, we have a film of vapor flowing upwards. One has to flow downwards because the liquid is heavier. Here this has to flow upwards because the vapor is lighter. But keeping this similarity in mind, Bromley derived an expression for the heat transfer coefficient. Basically, Bromley did a derivation very similar to what the Nusselt derivation was like, which we talked about when we studied condensation. So, you see the similarity of the expression now. The expression obtained by Bromley was H c is equal to 0.62 into bracket lambda prime lambda dash to rho v into rho l minus rho v g k v cubed divided by T w minus T s mu v into d, the diameter of the tube, the whole thing to the power of 1/4. You will see it is very similar to the expression we had in condensation, which was lambda rho squared g k cubed upon T w minus T s minus T w into mu d. Very similar, excepting that instead of the properties of the liquid, now you have the properties of the vapor. You have mu v, k v, rho v, and then you have a rho l minus rho v because you have buoyancy, you have the liquid moving, the vapor film moving upwards. You also have, instead of lambda, you have lambda dash. And what is lambda dash? Lambda dash is the difference between the enthalpy of the vapor at the mean film temperature T w plus T s by 2 and the enthalpy of the liquid at saturation temperature. This is the definition of lambda. So, it is not just latent heat of vaporization, it is a latent heat plus an enthalpy of vapor associated with superheat of the vapor. That has to be taken into account. Now, when you have a film of vapor surrounding that tube and the temperature difference T w minus T s, now mind you, is going to be high. If you recall the curve I showed you last time, I mentioned that in stable film boiling the value of T w minus T s can easily be a few hundred, if not a few thousand. Let me go back and show the typical pool boiling curve of last time. We are talking of this region, the stable film boiling region, where T w minus T s is in hundreds. Now, when you are in this region and you have a vapor film, obviously, radiation across the vapor film is also going to be an important factor, and we have to therefore take that into consideration. So, what Bromley did was, doing a Nusselt type of analysis, he derived what he called as a convective heat transfer coefficient. Then he went on to say radiation is also important, and said since radiation is significant in film boiling because of the high values of T w minus T s, the radiation component has to be added on in order to obtain the total heat transfer, and he showed that the total heat transfer coefficient is the convective heat transfer coefficient H c plus 3/4 times the radiative heat transfer coefficient. Whenever H r is less than H c, he showed that this expression is valid within the accuracy that one wants. We will not go into the details, I am just asking you to accept this. I am saying calculate the convective heat transfer coefficient from the expression which Bromley gave earlier, which I have shown you, that is this expression, all right. Then calculate the radiative heat transfer coefficient by using formulae for radiant heat exchange between parallel planes, taking the emissivity of the liquid to be unity. So, H r is the radiation heat transfer coefficient calculated from the formula for radiative heat exchange between parallel planes, taking the emissivity of the liquid to be unity, and then say that the total heat transfer coefficient is H c plus 3/4 H r. That is what I am asking you to do. So, this is how one would calculate the heat transfer coefficient in stable film boiling. All vapor properties are evaluated at the mean film temperature. All vapor properties means mu v, k v, etc., that we need, all vapor properties are evaluated at the mean film temperature. The liquid density is evaluated at the saturation temperature. So, this set of equations, the convective heat transfer coefficient and the radiation heat transfer coefficient, appropriately added on, gives us the total heat transfer coefficient. Now, let us do a few problems to illustrate the use of these correlations which I have given you. We will first of all do the following problem. Problem is the following. We say there is a pool of liquid, a 0.1, let me read it out, a 0.14 centimeter diameter horizontal platinum wire is held in a pool of saturated water at 100 degrees centigrade and 1.013 bar. This 100 degrees centigrade corresponds to this saturation pressure. The wire is electrically heated so that boiling occurs. Calculate Q by A when the temperature difference T w minus T s is 1 degree centigrade. Calculate T w minus T s when the temperature difference is 15 degrees centigrade. That is the problem. So, let me just draw a pool. Let us say we have a pool of liquid like this. This is our pool of liquid. Like this. And we are told that it is at 100 degrees centigrade T s, it is a saturated pool at 100 degrees centigrade. In this pool, I have a horizontal heated platinum wire. Let us say this is the wire shown in red here. This is the platinum wire. which is electrically heated. I would like to know for T w minus T s, and T w is the temperature, surface temperature of this wire, platinum wire at T w. So, the problem is, if T w minus T s is 1 and 15, what is Q by A for these two values of T w minus T s? That is the problem. It is a straightforward substitution into the correlations for natural convection and for nucleate boiling. So, let us do the problem now. Let us, in the first case, we will make the assumption for T w minus T s, let us do that first, equal to 1 degree centigrade. We will assume that we are in the natural convection region, which is a good assumption. Up to a few degrees, this is usually true. We are in the natural convection region in pool boiling. So, if I am to use a natural convection correlation, I will use the single phase correlation for horizontal wires, which I showed you earlier. What do I need for doing calculations now? I need first the mean film temperature. Now, systematically I will go about the calculation. I will say mean film temperature is equal to 100 plus 101 by 2, which is equal to 100.5 degrees centigrade. The properties of water will be, which if you look up, you will get at the mean film temperature would be beta. You need the expansion coefficient, you need the kinematic viscosity, you need the thermal conductivity, and you need the Prandtl number for substituting into the correlation. The values, if you look up in a table, you will get the following. For beta, Kelvin to the minus 1, nu is 0.294 into 10 to the minus 6 meter squared per second, thermal conductivity 0.683 watts per meter Kelvin, and the Prandtl number of the liquid 1.74. These are properties which you look up for water at 100.5 degrees centigrade. Calculate the Rayleigh number now. So, you get the Rayleigh number RAD is equal to GRD PR, which is equal to G beta T w minus T s d cubed divided by nu squared. This is the Grashof number with d as the characteristic dimension, divided by nu squared, the whole thing is the Grashof number multiplied by PR. Substitute the numbers which we have got, and I am skipping the substitution step. You will get in this particular case 409.1. Now, go to the correlation for natural convection, and you will get Q by A is equal to 0.683, which is K for water, divided by D 0.14 into 10 to the minus 2, that is the diameter of the wire, into T w minus T s 101 minus 100 multiplied by the correlation is 0.36 plus 0.518 multiplied by the Rayleigh number to the power of 1/4, the whole thing divided by 1 plus 0.559 divided by the Prandtl number 1.74 to the power of 9 by 16, the whole thing to the power of 4 upon 9. This is the correlation for natural convection. I am just substituting, it is nothing very deep. And if you calculate this, you will get 1117 watts per meter squared. So, this is the first answer that we are looking for. We are saying for a temperature difference of T w minus T s equal to 1, we are likely to be in the natural convection region. So, we have used natural convection correlation for single phase for a horizontal wire and got the Q by A, which we would need in the heat flux we would need to supply for this particular temperature difference. Now, let us go on to the next part. The next part is calculating the Q by A for T w minus T s equal to for T w minus T s equal to 15 degrees. That is the second part. Quite obviously, we are now going to be in the nucleate boiling region. For this particular T w minus T s, assume nucleate boiling. Nucleate boiling usually starts 3, 4, 5 degrees centigrade for water, may go up to 20, 25, 30 degrees for water. Assume nucleate boiling. Now, we will need for using the, we will use the Rosenau correlation, and in order to use the Rosenau correlation, we will need properties at the saturation temperature 100 degrees centigrade. And what are the properties? I will just put down the values and then just say what the answer will be. You will get, if you look up the properties of water at 100 degrees centigrade, you will get Cpl equal to 4220 joules per Kelvin, joules per kilogram Kelvin, mu L, the viscosity equal to 282.4 into 10 to the minus 6 kilograms per meter second, sigma, the surface, the liquid vapor surface tension 589 into 10 to the minus 4 newtons per meter, density of the liquid equal to 958.4 kilograms per meter cubed. Then we will need the density of the vapor rho v. So, we will get from the table rho v, density of the vapor 0.598. If this is not available in the liquid tables of giving the properties of the liquid, you may have to go to steam tables, 0.598 kilograms per meter cubed, and the Prandtl number of the liquid equal to 1.75. You will also need the constant KSF. So, go to the table which I showed you, the constant KSF is for this particular case platinum and water 0.013 from the table. So, we have got all the values. Now, it is a straightforward substitution into the Rosenau correlation. Substitute into the Rosenau correlation. Substitute into the Rosenau correlation. I am now skipping the steps, I am not going to substitute all these numbers, but if you do that, you will get Q by A is equal to 141.32 multiplied by 115 minus 100, this is the temperature difference T w minus T s, the whole cubed, and that comes out to be 476,955 watts per meter squared. Notice the steep increase in the value of Q by A when TW minus TS has gone up from 1 to about 15. We have gone up by an enormous factor. Earlier the Q by A in natural convection was only about 1000, now it is 476,000. And just to illustrate that, let us go back again, look at the pool boiling curve. Notice it is a log plot here. This is the natural convection region. So, our first point was somewhere here, which we were calculating, some region here. Now, we are calculating a point which is somewhere here, and it is a steep rise where Q by A is proportional to TW minus TS to the cube power. So, our first point that we have calculated is somewhere here in this problem. The second point that we are calculating is somewhere here in this problem. Keep that in mind. Okay. Now, so this is our second answer. These were the two answers we were looking for. Use appropriate correlations to calculate Q by A for different temperature differences. Now, let us do one more problem in film boiling, so that we illustrate the use of Bromley's equation. The problem we are going to do is the following. The problem is an aluminum cylinder 2 centimeters in diameter and 15 centimeters long is heated to a temperature of 500 degrees centigrade and immersed horizontally in a liquid nitrogen bath at minus 196 degrees centigrade. Liquid nitrogen has a saturation temperature of minus 196 degrees centigrade at around atmospheric pressure. Neglecting heat transfer from the end phases, calculate the initial heat transfer rate. Take emissivity of the aluminum surface to be 0.4. So, this is the problem which we want to do next. Now, here is the solution. The first thing to note is the surface of the aluminum cylinder, which is heated, is at 500. The liquid nitrogen is at minus 196. So, when you immerse the cylinder in the liquid nitrogen horizontally, you have got a temperature difference initially of 696 degrees centigrade. At that temperature difference, you are going to get stable film boiling. That is what you are going to get. So, that is the first thing to recognize. So, we are going to use the equations for stable film boiling. So, here is our pool of liquid, which I am showing in this sketch. Here is the heated aluminum cylinder at 500 and this is the saturated liquid at minus 196. So, stable film boiling is going to occur. So, if I look in the cross section of this is my aluminum cylinder and around it a film of vapor is going to form like this and rise to the surface. A plume is going to rise to the surface. We want to calculate the heat transfer coefficient. It is again a straightforward substitution. So, let us go through the whole procedure. The first thing to note is the mean film temperature at which we will need properties. Mean film temperature of the vapor equal to 500 plus minus 196 by 2, which is 152 degrees centigrade. So, we will need properties of the vapor at this temperature. In this case, the particular vapor is nitrogen, it is liquid nitrogen. So, nitrogen gas, we have to look up these properties, has the following properties. You have to look them up in the property tables for nitrogen, has the following properties at 152 degrees centigrade. You have Kv, the thermal conductivity 0.0349 watts per meter Kelvin, rho v is equal to 0.80 kilograms per meter cubed. Mu v, the viscosity 23 into 10 to the minus 6 kilograms per meter second. Also, we will need the CPV, the average value of the specific heat of the vapor, which is 1048 joules per kilogram Kelvin. We will also need the density of the liquid at minus 196, which is 800 kilograms per meter cube, and we will need the latent heat of vaporization for nitrogen at that particular temperature, which is 201 into 10 to the power of 3 joules per kilogram. One has to look up all these properties in appropriate property tables. I am giving you the values here. Now, we calculate first of all lambda prime. Lambda prime is the latent heat plus the enthalpy associated with the superheat. So, 201 into 10 to the power of 3 plus the average specific heat of the vapor multiplied by 152 minus 196, that is at the mean film temperature, and this will come out to be 565.7 into 10 to the power of 3 joules per kilogram. Then substitute into the Bromley equation, and now I am not going to do the substitution, I am just going to give you the result. If you substitute into the Bromley equation, substituting into the Bromley equation, I am skipping putting down the details of the numbers, you will get H c is equal to 91.34 watts per meter squared Kelvin. So, I want you to do this calculation on your own with the property values I have given. Now, we have to calculate HR. Calculate HR. HR means I need to know the heat, the flow of heat by radiation. Q by A radiation, I use the formula for parallel plates. Q by A by radiation is the Stefan-Boltzmann constant 5.67 into 10 to the power of minus 8, T w to the power of 4, 773 to the power of 4 minus 77 to the power of 4 divided by 1 upon 0.4, 0.4 is the emissivity of the aluminum surface, 1 upon 1 is the emissivity of the liquid minus 1, which comes to be 8096.9 watts per meter squared. And now, from this I calculate HR, So, I will get HR is equal to the heat flux in radiation 8096.9 divided by the temperature difference 773 minus 77, which comes out to be 11.63 watts per meter squared Kelvin. Therefore, the total heat transfer coefficient is H c plus 3/4 HR, which is 91.34 plus 3/4 into 11.63, which is equal to 100.07 watts per meter squared Kelvin. This is the total heat transfer coefficient, and therefore, the initial heat flux or the initial heat transfer rate, rather, that is what we are asked to calculate. The initial heat transfer rate is equal to the heat transfer coefficient multiplied by the temperature difference 773 minus 77, this gives the heat flux, multiplied by the area pi into 0.02 multiplied by 0.15, and this comes to 600 and 56.4 watts. We are neglecting, as we are told, neglect the heat transfer from the end faces of the horizontal cylinder. So, this is the answer we are looking for. We have done it in steps, remember. We calculated first the convective heat transfer coefficient using the Bromley equation, then we calculated the radiation heat transfer coefficient, we added them up with the formula given and then got the total heat transfer rate. Now, let us just sum up for 1 minute what we have done in this topic. In condensation and boiling, under condensation, we did drop in film condensation, we did film condensation on a vertical plate and film condensation on a single horizontal tube and a bank of horizontal tubes. In boiling, we first described what is pool boiling and flow boiling. We discussed a typical pool boiling curve. We then did various types of pool boiling while we were discussing the curve and then gave correlations in the saturated pool boiling region for natural convection region, for the nucleate boiling region, for the stable film boiling region and correlation for the peak heat flux. And finally, we did some problems today to illustrate the use of these correlations. With this, we have come to the end of the topic of condensation and boiling.